In this video, we're going to be discussing chapter 9, which is solutions, and the topics that we're going to be talking about in this chapter are talking about solutions, defining what a solution is, and then we're going to talk about electrolytes and non-electrolytes and how to distinguish between the two and their importance. And then solubility, how do you define solubility? And then solution concentrations. What type of solutions are prepared? Each type of solution has a particular definition. So here we're talking in terms of amounts, and then we'll apply it to reactions. And so there will be stoichiometric calculations involved. And then finally, we are going to look at dilutions of solutions. How do we determine the final concentration of the diluted solution? And the last topic would be properties of solutions. In particular, what happens to solutions when solutes are present in them in terms of boiling points and freezing points, etc. All right. So the first two topics, let's deal with that, defining what the solutions are, and then talking about electrolytes and non-electrolytes. Okay, so here in this picture, you have a nurse working with a patient who's undergoing dialysis, and dialysis is based on a principle called as osmosis, whereby all the excess waste products are removed. So the blood is purified, and then the purified blood is pumped back when the kidneys are not functioning properly. So some of the skills that are going to be carrying over from chapters 1, 2, 6, and 7 is again solving the equations, conversion factors, equalities, and then this is important from chapter 6, applying what those attractive forces are, especially hydrogen bonding, and then the dipole-dipole interactions. And then using stoichiometry, especially after we learn chapter 7, and applying mole-mole factors. So what exactly is a solution? So solution has two things in it. It has the solvent. Solvent is always going to be something which is in larger quantity. So remember that. Solvent, large. Solute is the smaller quantity. All right. So here you see a sodium chloride solution where the sodium chloride is being added to water. So water is in the larger quantity, that's the solvent. The solute is in the lesser quantity, and so the sodium chloride, the salt, is the solute. Now it doesn't always have to be colorless solutions or solids in liquids. It can be all kinds of various different types of solutions. All right, so you can have a liquid in liquid, like for example vinegar would be a liquid in liquid because you have acetic acid, which is a liquid, and added to water, another liquid. All right, or you can have gas in gas like air, where oxygen and all the other gases are the solutes, and nitrogen, which is 78% of air, that's the solvent. Or you can have a solid in solid, such as the alloys like brass, or even the penny, the copper penny, the present day copper penny, which has a lot of zinc. All right, so it's a combination of zinc and copper. And so the larger quantity of one component would be the solvent, and the lesser would be the solute. So a true solution is where the solute and the solvent are homogeneously mixed together. All right, and usually what happens is when they're mixed well, you cannot tell one from the other. For example, once sugar or salt is mixed into water, you really can't tell which is pure water and which is a mixture, because unless you boil the water, you and then it leaves behind a solid residue as an evaporation, or you can't just use filtration unless you have a heterogeneous solution like a muddy water. Then you can use filtration. But a true solution where the solute particles are so small and evenly distributed, and the solution kind of looks very much like like a liquid which doesn't have anything in it. All right, you can't see the stuff that's mixed in. Then you would require a technique like evaporation to separate out the solute from the solvent. Okay. Sometimes, a lot of solutions made in water, water is the universal solvent, but sometimes you can have a solute which is highly colored, all right? And so you can have a colored solution. It doesn't have to be colorless all the time. So like here, copper sulfate solution, copper 2 sulfate solution is a blue, intense blue colored solution, all right? So when you have a very concentrated solution, it's a deeper blue. When it's more diluted, more water is added, it becomes a lighter blue. And what happens is, you can see the solute is the copper 2 sulfate, which is kind of interspersed between the solvent, which is the water molecules. All right. So table 9.1 is showing different types of solutions that can be present: gas in gas, as I mentioned, air, or gas in a liquid like soda, or ammonia, liquid in liquid vinegar, I mentioned that, solid in liquid, salt water, or iodine, which is dissolved in ethanol, or solid in solid like the alloys brass, steel, that's carbon and iron. So iron is the solvent, that's in larger quantity. Brass is zinc and copper. Copper is the solvent because that's in the larger quantity. So here you can see the reason why water is called the universal solvent is because of hydrogen bonding. Remember, I mentioned about bonding when we talked about bonding in chapter 6, and especially hydrogen bonding, which is between oxygen and hydrogen because of the difference in electronegativity. And so this is an intermolecular force of attraction between neighboring water molecules, which is why it's very strong, which is why water has a high boiling point. Now, if there is a compound that is polar that also has the FON group, remember FON is hydrogen directly bonded to oxygen or a fluorine or a nitrogen. So if you add some HF to the water, or a sugar which has these OH groups, then that sugar would also hydrogen bond to the water. So basically anything that is got a charge, polarity, like water does, would dissolve in water. So the principle is that like dissolves like. All right. So here in this picture, you have two solvents. You have water up here on the top, and a more denser solvent like carbon tetrachloride, which is non-polar. If you recall, the CCl bond is polar, but however, CCl4, carbon tetrachloride, is non-polar. Now, when I add some iodine, I2, which is non-polar, it doesn't dissolve in the water, but it sinks down and it dissolves here in the carbon tetrachloride portion. And so you see that non-polar solute will dissolve in a non-polar solvent. Whereas if I had added nickel 2 chloride, which is an ionic solvent, a polar ionic solute, excuse me, a polar solute, then it dissolves into the water. All right. So ionic compounds or polar compounds will dissolve in water, whereas non-polar compounds would not dissolve in water. So like dissolves like. All right. So you see, if it's polar solute, then it will dissolve in a polar solvent. If it is a non-polar solute, it will only dissolve in a non-polar solvent. All right. So non-polar solutes, oil, cannot dissolve in water. All right. A polar solute like sodium chloride cannot dissolve in an alcohol or carbon tetrachloride or any other non-polar solvent. So what happens when an ionic solid that can dissolve in water, like such as table salt, sodium chloride, is added to water? As you can see, you're adding a big chunk of the sodium chloride, all right? There's lots of sodium ions and chloride ions all bonded together by ionic bonds. However, water is able to overcome this force of attraction between the positive sodium ions and the negative chloride ions. So literally it chips away at this big chunk of sodium chloride and pulls each ion apart. So you can see that each ion is being surrounded by water molecules, forming a little cushion, preventing the sodium and the chloride ion from coming back together and clumping up. So they remain separate because of this. And you can see that the negative part of water, the oxygens, are surrounding the positive sodiums, and the positive part of water, the hydrogens, are surrounding the negative chloride ions. So again, here, the reason why sodium chloride is able to dissolve into water is because, again, of these attractions between opposite charges. All right. Okay. So which is why it leads to, again, that saying that like dissolves like. Now, once the ions are pulled apart, they can't come together, and that's why they remain dissolved into the water, and that's why this term AQ or aqueous, which means dissolved in water, is used. All right. So they're solid on the reactant side. Once they dissolve into the water, they become AQ and separated as ions. So here you have solutes such as methanol, which is polar. It can dissolve in water. And unlike sodium chloride, it doesn't separate into ions. There are no ions in methanol. However, because of the presence of the OH bond, methanol can hydrogen bond within itself, like water can hydrogen bond between the water molecules, but methanol can also hydrogen bond with water. All right. The negative part of methanol, the O part, hydrogen bonds with the H of water, and the H of water is hydrogen bonding with the O of methanol. All right. So they can hydrogen bond within themselves, but when dissolved into water, they hydrogen bond with water, which makes it soluble. All right. So something that is polar, like methanol, can dissolve in water due to hydrogen bonding. However, no ions are formed. Okay. So compounds which contain non-polar molecules like iodine or oil will not dissolve in water, all right, because there's no attractions to make them soluble into water. Okay. All right, we will stop here.